So where we ended on Thursday was looking at the balancing of redox half reactions. So this is a more advanced version for balancing. It really only works for your half redox reactions. Okay, so we'll split it into half a reaction at a time. So what we end up doing is looking at our reactants and say, okay, I see tin and I see iron. And now what I'm going to do to split is I want to look to the product side and say what looks most like each of those reactants. So I look at the product side and I see tin again. Okay, so those two should be paired with each other. And I see iron again, so those two will be paired with each other. So what I end up doing is pulling it out and saying, okay, I've got tin plus 2 going to tin plus 4, and I have iron plus 3 going to iron plus 2. So it's the intent. We're just separating it out, almost like factoring an individual number. So if we were given the number 6, we could factor that into 3 and 2. Okay, so it's kind of that idea. It's a little bit different because what we're going to be doing is addition, so it's more like it's saying it's 4 plus 2 to get 6. It's the same principle at least. So when we pull this out, we've got our two separate equations now. And now what we'll do is ignore half of them. And we'll just look at one. So I'm going to cross out the tin for the moment, and we're just going to look at the iron. Well, our iron equation is not balanced due to the charge. On our left-hand side of the equation, we have a plus 3, and on the right-hand side, we have a plus 2. So we can't create or destroy matter, which means we can't create or destroy charge, because charge is ultimately electrons. So we now need to add electrons to our equation to make sure that these charges balance. It's really a 50-50 shot. Either the reactant side or the product side needs the electrons. Okay, we can't subtract electrons, but we can add them. So let's take a guess and say, well, it needs to be on the product side. So I'm just going to add one electron and see what happens to the charge. Well, I didn't do anything to the reactant side, so it's still a plus 3. The product side, iron was a plus 2, and if I add an electron, the electron has a -1 charge, as seen in the upper right-hand corner. So I would then subtract 1, or add a -1. The result is the overall charge on my product side is 2 minus 1 plus 1. Well, charge has to be the same on both sides of the equation. It's definitely not the same right now. Okay? So what we do is guess, say, okay, it's got to be the product side, and then we look at our numbers and say, did we get closer to our numbers being the same, or did we get further from our numbers being the same? Well, we were plus 2 and plus 3, and now we're plus 1 and plus 3, so we got further away from those numbers equaling each other, or charges equaling each other, which means that my guess of putting the electron on the product side was wrong. So that just means let's erase all of our work, go back with our charges. We had iron plus 3, iron plus 2. Let's go ahead and add that one electron on the reactant side. And now when we go through and look at our totals, we have a -1 plus a positive 3, which equals plus 2. So on my reactant side of the equation, I have a plus 2 overall charge, and on my product side, I have a plus 2 overall charge. Okay, so these are charges, not oxidation states. Since my charge is balanced, my equation is now balanced, and I can go ahead and now move on to the next equation. So we'll free up our tin, and now for your sake, what you would do is just cover it up, your other equation, because we don't care what's happening with it, at least not yet. We're just going to cover it up and move on to our tin. So it's still correct what we did, I'm just covering it. So now when we look at the tin, do the same idea. On the reactant side, we have a plus 2 charge, and on the product side, we have a plus 4 charge. Okay, well, our charges don't equal each other, so we need to balance it. So again, let's guess. Well, it was on the reactant side last time, so maybe we can put an electron on our reactant side. So we put that there. Our charge is a -1 plus a positive 2. This gets us what overall charge? Well, a plus 1. Okay, what were we trying to get to? It needs to equal a plus 4. Does it equal? No. Okay, did we get closer or further from the charges being the same? Well, we got further from the charge being the same, which means we guessed wrong. Oh well, erase all of your work and go ahead and put the electron on the other side. Now that our electron's on the other side, we can go through and look at our charges. +2, +4, plus a -1. Charge on the product side equals +3. Okay, our charges don't equal each other, but did we get closer to balancing out the charge? Okay, you should see that we went from 4 to 3, and 3 is closer to 2 than is 4. So we did get closer, but we didn't get quite close enough. So again, to balance, we'll add electrons. So I can add another electron. And I'm going to add it to the product side because that was where I was getting closer to our charge. If I now add yet another electron into this, so plus another -1, this gets me +2. So now my charges do balance. My product side I have a +2 charge, and on my reactant side I have a +2 charge. Okay? So my equation works as I've got it drawn. It's a bit repetitive to say +1 electron, +1 electron. So what we'll go through and do is switch this around to say it is +2 electrons. Okay, just to simplify it. Now that we've got our electrons all into our equation, we can now go ahead and look at our overall reaction. Okay, and with our half reactions, just like when we broke up 6, we're saying is if we had 6 as our answer, that came from 4 plus 2. Right? So we're going to do the same thing with our equation above. We just bring down everything that's unique. So it would be 1 electron plus 1 iron plus 3 plus 1 tin plus 2 goes to iron plus 2 plus tin plus 4 plus 2 electrons. Okay, so we're just adding it together. We don't have to worry about balancing anything yet. Now what we do is look across that reaction arrow. So let's highlight that reaction arrow. There's our reaction arrow. Did anything show up the same on both sides of the equation? Okay, well, you may say that you see Fe show up on both sides. And you're right, you do see the symbol Fe. But is that symbol connected to anything else? It is connected to that charge. So if I'm going to say iron shows up on both sides of the equation, I have to make sure Fe plus 3 shows up on both sides. And in this case, if we look to the other side where we have our iron, we have Fe plus 2. So we can't cancel the iron because they're different. Okay? Plain and simple. They aren't the same. However, if we take a look at what we start with here, 1 electron and 2 electrons, ultimately it's the same thing. It's just an electron. So I can condense those two terms just like we would do in normal math. We go ahead and subtract 1 electron from both sides, and we could end up with or end up canceling the electrons on the reactant side, and we'd end up with just 1 electron on the product side. Okay, so what we've done is just added the equations and then simplified. So our result is we end up with an overall reaction, okay, with 1 electron. When we started this whole process out, we said that this equation wasn't balanced. The charges did not balance. Okay? Well, if we look at it now, we should see that the charges do balance. Okay? So reactant side, take the charges of every species there. We have a +5. We look to the product side, look at the charge of all of our species. We have a +5. So our charges do balance. We might say, oh, okay, great, it's now balanced. We don't have to worry about it. However, there's a big issue. Electrons are highly, highly, highly unstable, which means in a balanced equation, there are no free electrons. That means the electrons cannot exist on their own. We can't see them either as a reactant or as a product. And you might say, well, in the half reactions, there's an electron as a reactant and there's an electron as a product. You're right, in the half reactions we can show them. But remember, we cannot do a reduction reaction unless we also do an oxidation reaction. Okay? And the reason being is that the electrons will cancel in our overall reaction. So the reduction and the oxidation are only half of a reaction. We're allowed to have electrons there because that reaction is by definition not possible on its own. Only when we put them together can we say, oh, there's an electron, something's wrong. Okay, and that's how we have to then go through and fix this. So now we have to look at our problem and go back to our initial statement. Okay, so no electrons ever in a completed, fully balanced equation. Whoops. Okay, so how can we go through and fix this? So somehow or another, when we add these two equations together, okay, when I add my reduction to my oxidation, I need my electrons to cancel each other. And there's really only two ways that we can go through and do this. I can go ahead and run my oxidation reaction half the number of times, okay, which means I'd be multiplying a half through. So I get half the number of electrons. Okay, a half times 2 does give me 1, but then that half also has to apply with where those electrons came from, which was the tin. And if we go with our simple understanding of our equations, can we have half of a tin atom? No. Okay, half of a tin atom isn't tin anymore. That would be an entirely different element. Okay, so that half multiplication doesn't work. Okay, so let's back all the way out of that. So we can't do our half. So the only other option that we can do is run our other reaction twice. So we'll run it 2 times. So 2 times 1, whoops, looks like 21. Let's try that again. 2 times 1 electron gets me 2 electrons. 2 times 1 iron gets me 2 iron atoms. Well, am I allowed to have 2 iron atoms? Sure, why not? Okay, that just says I have 2 of them. I just have more of the same atom. That's fine. And I'll have 2 times my iron plus 2 atom. Okay. The equation is still balanced. We have 2 irons on both sides of the equation. Okay. And if we look at our charges, what happens with our charge? I don't know, I wanted to erase that, but I did anyway. We have 2 negatively charged species, so a negative 2, plus 2 positive 3 charged species, so a plus 6. And on our product side, we have 2 positive 2 charged species, which is a plus 4. Well, negative 2 plus 6 equals plus 4. Our equation still balances. Okay? We had to go through and put in those extra coefficients because what we're trying to do is make sure our electrons cancel. So the goal is to make sure our overall, both the reactant side and the product side, must be permanently balanced. Okay? And that is a bit of a challenge, okay, particularly with our redox. But it's the same concept that we've already been dealing with, except now we actually have to multiply an entire equation by 2 and not just do little pieces. Okay, so it's a bit tricky. So there's the idea. We run the reduction reaction twice. So we multiply everything through all of the coefficients within that one half reaction by 2. Now when we add up our equations, the 2 electrons on the reactant side will cancel with the 2 electrons on the product side. And when we add our 2 equations together, we get this overall equation. Okay, well, if we did this right, our charges should balance. Okay, and our atoms should balance. So let's take a look at the atoms. How many tin atoms do we have on the reactant side? 1. Then on the product side? 1. Tin's fine. How about the iron atom? How many iron atoms do we have on the reactant side? 2. And on the product side? 2. So it balances, okay, as far as the atoms go. Now the trickier part when we deal with redox is looking for the charge. Okay, well, our tin is a plus 2 charge. Our iron's a plus 3 on the reactant side, but there's 2 of them, so it's a plus 6 charge contribution. So we're looking at the overall charge between all of the atoms present. If we look to our product side, we have 2 iron plus 2 atoms, which means we have a plus 4 charge. And if we look at the tin, our tin is a plus 4. Right? If we go through and now compare across the reaction, do our charges equal? Well, on one side I have an overall plus 8 charge, and on the other side I have a plus 8 charge. So my charges do indeed balance as well. So as long as my charges now balance and my atoms balance, my equation has been balanced. Okay? And there are sneaky ways in which I can get through and ask this type of question without actually making you go through and balance the whole thing. So one of the things you're going to have to watch out for is all of these individual steps. So for instance, I think it'll show up in one of our later examples, which I think are on the next slide. Let's go ahead and ask it now. Sum of the coefficients. So we could ask the sum of the coefficients for the balanced equation. Okay, and I can tell you right now, two answers that will be present will be A, 4, and as a B choice, we'll have 6. Okay, we'll probably also throw in a 2, and why not, let's give you a 1, just for the heck of it. Right, if we look at those choices, 4, everybody goes, well, look at that first equation. So if I gave you this equation and said, what's the sum of the coefficients of the balanced equation, you might immediately jump to 4 because it looks balanced, except the charge isn't balanced, which means A cannot be correct. Well, at least as a first pass, probably isn't correct because our charge isn't balanced. You would have to go through this entire process of all of these half reaction stuff to look at your balanced equation and now look at the coefficients in front. 1 plus 2 is 3, plus another 2 is 5, plus 1 is 6. Your answer is B. You have to go through all of that redox reaction balancing to make sure it comes out correct. Okay? Another question I could go through and ask. Okay, so instead of making you go through all of the work, I could go through and say, how many electrons are transferred? Okay, so I'll say that again, I'm not going to rewrite it. How many electrons are transferred in the course of this reaction? So again, we're going back up to this first reaction up here. Well, one answer, tell you right now, will be 0. Because you look at that equation, do you see any electrons? No, so you say, oh, it's 0. Another answer will be 1. Okay, because when we first balanced our iron equation, we needed 1 electron to balance it. Another answer, 2. Another answer, 4. Right? So the 0 we just talked about doesn't make sense because if we look at our equation, the charges don't balance. We need electrons to balance this, so we have to have electrons through it. 1 electron being transferred. Before we went through and did our balancing, in the reduction reaction, we only needed 1 electron, but that's just to run the reduction, not the overall equation. If you're asked to do the overall equation, you have to consider everything, which means 1 isn't the right answer either, because that is just for the reduction. We now run into an issue with 2 and 4. Okay? Common mistakes. I see 2 electrons on the reactants and 2 electrons on the products. Well, I know 2 and 2 is 4, so answer must be 4. Careful. They're on separate sides of the equation. Remember, they canceled each other out, which means it's not 4 electrons transferred. It's 2 electrons transferred. Okay? The tin gave up 2 electrons. Those 2 electrons were absorbed by the iron. So only 2 electrons were transferred in this process. Okay, so you got to be a little bit careful with how you go through and approach these types of problems. There's tons of different ways we could ask the same or different questions, but get at the same idea and the same work. Okay? So here's some balancing practice. I'm not going to go through and do these for you. I'm going to leave you guys to go ahead and attempt these, and we'll talk about it when we get into class on Tuesday. And worst case, you may even push into Thursday, but we'll see this balancing for sure on Tuesday. One last reaction type. I definitely put this slide in the wrong spot, but we have one more reaction type before we even get back to the basic ones. It does actually kind of belong in our redox section. We can look at a combustion reaction. And some of you may already know what a combustion reaction is, because probably most of you got to campus today using a combustion reaction. And in fact, most of you are living right now because of a combustion reaction. What we're looking at is the reaction of an organic material with oxygen to produce carbon dioxide and water. Our cars are combustion engines. They rely on burning gasoline to turn into CO2 and water. The high temperature released makes sure that the water comes out as a vapor or a gas state, and so we start with something in a relatively small volume that then expands rapidly into a large volume. That rapid change in volume we use to cause our cars to move forward. So our cars move that way. But if we think back to what we do to actually survive, in theory, everybody right now, as you're listening to this video, is also combusting. What? You're not blowing up? You're not on fire? That's true. Your insides are technically on fire. You are breathing in oxygen. The oxygen reacts with organic materials within your body. Your body uses a slow, controlled combustion of that organic material to generate energy, which we use to live. So all forms of life that we really deal with or that we're aware of so far use some kind of combustion reaction. So let's look at an example. We could take CH4 and react it with oxygen gas. Okay. This is going to produce CO2, our carbon dioxide, and water. Okay. Relatively straightforward. All we're doing is converting it in. The next question is going to come, is the equation balanced? So we still have to go through and balance it. So we'll use the same ideas that we've been using. We'll start with carbon. Reactant side it's 1, product side is 1. Balanced. We can then move to hydrogen. Reactant side it's 4, product side it's 2. Well, that's not balanced. So what do we need to do? We'll make sure that 2 becomes a 4 by putting a 2 in front of our water molecule. Okay, so we're now getting pretty close. We can move to our oxygen. Our oxygen is 2 on the reactant side, and our product side it is, think about this one, 4. The 2 of our coefficient applies to both the hydrogen and the oxygen, and our 2 of our subscript applies just to that oxygen. So we have a total of 4 oxygens on our product side. Well, that's not balanced, so what do we do? That 2 needs to become a 4, and we'll do that by putting a 2 in front of our oxygen. Now we actually have our balanced equation. Well, actually no. Let's check that. Now we go through and check. How many carbons? 1, 1. How many hydrogens? 4 and 4. How many oxygens? 4 and 4. How many carbons? 1 and 1. Hydrogens, oxygens. Check it again, check it again, check it again. Okay, and you now have your balanced equation. Okay, the question that we could ask, let's go ahead and throw in a different one this time. What is the coefficient for the balanced equation for oxygen gas? Okay, well, the first thing you should do with this question is write down some information about this. Okay, so we want the coefficient. This is number in front. Okay, for balanced, okay, atoms have to equal each other. Okay, for oxygen gas, well, what is oxygen gas? Oxygen gas is O2, okay, by itself. So now that we know this information, we can go back to our equation and say, well, did we balance it? Yep, all of our atoms equal each other. We want the oxygen gas, so here's our oxygen gas. The coefficient for that is 2. Okay, so our answer would be 2. What would be our possible answer choices? 1, 2, 3, 6. Let's throw in a 3, why not? Okay, all of those numbers can somehow be derived from our equation, okay, or from our final balanced problem. So you've got to make sure that you know that you're answering the question asked, not the question that you think is asked. This is why it's important when you go through and do the exam to write on the exam what you think is being asked. This way when you come back to check your work, you can look at your work and say, yeah, I agree with what I just said. I think the question is asking that. So now is my work correct for that question? Okay, so please do not be afraid to write on the exams. You should actually take full advantage of that. Okay, as one more example, let's see if I can actually make a more difficult one. I'm not sure I can off the top of my head. C2H4 plus oxygen goes to CO2 and water. Okay. So, starting with our carbons, let's see if I actually made this one more difficult. 2 on the reactant side, 1 on the product. So we'll make that a 2. And we now have our carbons correct. Hydrogens, we have 4 excuse me, on the reactant side, and on our product side we have 4 now by putting in our coefficient. Oops, so I may change that around. We had a 2 that we then became 4 because it's both the coefficient and our subscript adding to that hydrogen. Then we look at our oxygen, we've got 2, 4 plus 2, which gives us 6. To balance that, we need this side to become 6. We can do that real quickly with a 3. Okay, so I didn't make that one more difficult, so I'm going to try that again. I'm going to give it one more shot. If I don't get it in this one more shot, then I will come up with a more difficult one for class. Let's see what I can do here. I think I got it. So, carbons, 2 and 1. You can make the 1 be 2 by putting a coefficient in front. Hydrogen, we have 2 on our reactant side, and we have 2 on our product side. Hey, that was nice. It would actually balance better for us, isn't it? Then we go to oxygen. We have 2 on the reactant side, and we have 2 and 2, which gives us 4, plus 1 more, 5. There's no way we can make 2 equal to 5, is there? Actually there is. So what we can go through and do is say, this is a load of crap, I don't like it, so let's go through and do some pretty drastic changes on this. The first option, and I can't say I'm a fan of this, but it works. We can take that 5 and say, you know what, I need to have that 5 somehow show up on my reactant side, so I'm just going to put it in front of the oxygen. Okay. What does that mean I now have for my oxygens? Well, I should have 10 oxygens. Well, if we go to the product side, do I have 10 oxygens? Okay, no, I don't. Okay, so now I could try and go through and balance this out, which, by the way, I hate that method. That I don't like at all. Okay. Why could I go through and do this? Well, really what I'm trying to do is actually not just multiply by 5. I'm multiplying the entire equation by 5. So 5 times 1 for that first one is 5. 5 times 2 takes me to oh crap, I'm still recording with all the power of pause. Okay, so sorry, I just cleared everything up on here. I have to go through and show you the way that I know how to do it. I know there's a couple other methods for this, but I'm going to have to stick with the way that I know how to because that's how I can figure it out. So I need somehow to get 5 oxygens on my reactant side. So what I'm going to do, and this is going to be a bit freaky, I'm going to go 5 halves. Okay? That is going to end up turning the oxygens on my reactant side to be 5. Okay? Yes, that looks a bit crazy. We might wonder why I'm doing this. Okay, particularly because can we have 5 halves of an oxygen? Okay, can we have a fraction of an oxygen molecule? Not really. So because of that, I need to somehow cancel out that 2. How can I cancel out that 2? Well, I'll multiply it by 2. But if I multiply that by 2, I have to multiply the first one by 2, the second one, or our product, by 2 as well. Okay, so what does that mean? My coefficient now in front of the oxygen, 5/2 times 2 is 5. Coefficient in front of the C2H2, it would be 2 times what was there previously was 1, is now 2. 2 times 2 now becomes 4. 2 times our 1 becomes 2. So we just did a massive change of numbers here, and that's going to freak a lot of people out, and we did all sorts of fractions and things like that. So let's actually see if I did this right, because who knows, maybe I failed at this. So for carbon, I've got a coefficient and a subscript. My 2 needs to become 4 on my reactant side. On my product side, it's just my coefficient across, so my 2 again becomes 4. So far, not so bad. If we take a look at my hydrogen, I've got a 2 for a coefficient applying all the way through to it, and a subscript, so I have 4 hydrogens on the reactant side. On the product side, I have a coefficient and a subscript, and I also have 4. Holy crap, this is looking pretty awesome. If we go ahead and now move to our oxygen has a coefficient and a subscript. On my reactant side, I don't have 5 anymore, I actually have 10 oxygen atoms. And on my product side, I have a coefficient and a subscript, which gets me 8, plus another coefficient of 2, which gets me, hallelujah, 10. So sometimes your combustion reactions can be a bit of a beast. Okay? If you don't like the fraction method, that's fine, you don't have to use it. But you will need to come up with some other method to go through and balance it. And you'll notice that you get a lot of numbers or a lot of coefficients floating through our combustion reactions. Okay? So if it balances quickly and easily, great. If you don't balance it quickly and easily, you might just look at your multiple choice and pick a number that's really high and hope for the best. Okay? Or go through, read the textbook, talk to one of the tutors, see if they can give you a different method. Okay? Can't say I'm a fan of any other method. This fraction one just happens to be the one that's worked the best for me and the most consistently. So that's kind of how I have to go through and do it. Trying to teach you a different method isn't going to work from my perspective. Okay? And that's just for me. I apologize for that. So we'll go ahead and move forward. We'll finish up, whoops, I think I just double tapped. We'll finish up chapter 7 here relatively quickly because I need to go to a meeting. Double replacement reactions. We do need to be able to predict these. So we're going to put in reacts in quotes with these statements, and what we're going to try and do is convert these equations these words into an equation. So we have barium chloride, BaCl, and we know it's aqueous because we were told it was aqueous. Before we move forward, we need to make sure that our equation, or our formula, is balanced. Okay, the charge on barium is a +2. The charge on chloride is a -1. Uh-oh, doesn't balance. I need 2 chlorides to balance this. You should be starting to become an expert at going through and balancing your formulas. Okay, if you can't balance your formulas yet, keep working on it. You need that practice before you can start doing equations. Reacts with aqueous potassium chromate. So KCrO4, and we were told it was aqueous again. Potassium is a +1, chromate is a -2. I need 2 potassiums. Okay. In the double replacement reaction, we're swapping our ions around. So I will end up with potassium chloride. Potassium is a +1, chloride's a -1. So I don't care how many potassiums were on the reactant side or how many chlorides, I'm just taking the atom. Okay, the atom or the complex ion. So when I look at this formula, I have a +1 and a -1. My charge is balanced. That formula is correct. Okay. Again, balance just the atoms. Why is there a 2 next to the potassium in potassium chromate? That is to balance potassium with chromate. That's its sole purpose for being there. I do not bring that 2 over to the other structure because I'm not potassium chromate anymore. This is now potassium chloride. Okay, so there's no 2 coming across because the 2 is to balance chromate. Same issue with our chloride. We have a 2 with our chloride and barium. The 2 is there to balance the barium. If we go through and look at our product, the chloride does not have the 2 because it's not being balanced with barium. Okay? The only time your number translates across is going to be in this next part. We look at barium chromate. And I can already predict your question or your possible statement. So, well, the 4 from chromate transferred across. You're right. The 4 did transfer across. But why? Okay, you notice when we looked at Cl, the L transferred across. Okay, why did the L transfer across? It's the symbol for chloride. We need the L. Why does the 4 in our chromate travel across? Because the 4 is the same thing as the L. Okay? The L in chloride is the symbol for chloride. The 4 in chromate is necessary for it to be chromate. If you change that number, it's no longer chromate. It's part of the symbol for that name. Okay, so you do need to keep that. We look at our charges. Barium is a +2, chromate is a -2. Those charges balance, our formula is correct. Now we can go through and try and balance the whole equation. Okay, I'll leave you to go through and do that on your own, but what you should find is there's your answer. Okay? I'm actually going to have to stop the recording here, so you will see a second video also be posted here in just a little bit along these same lines, continuing from here. I just have to run off to a meeting now.